Okay, so I'm going to describe another library in HoTT, and I should be clear about the main difference between the last talk. So the main difference is that we're using higher inductive types and really are pushing the technology as far as we can, as opposed to being as conservative as possible. But I'll say this a bit slower. Yeah, I guess everyone knows this, of course, that we have an improvement of over the existing type theory and semantics in spatial sets. I also wanted to mention that there's now a proof of canonicity for homotopy type theory by Simon Newton. So there's the invariance axiom and the unimount library that we just heard about. The important difference here is that our hot library uses on, I should have said more clearly about it, who have contributed. So this is Andre Bauer, Jason Gross, Peter Lumseng, who's sitting over there, Mike Schulman, Mathieu Cezot, who's the head of the COC team, and myself. So a lot of the work focuses on high reductive types and the use of high reductive types, and also to see how, to experiment with the development of high reductive types. And this was also important in actually writing the book, that we could actually formalize these things and experiment with them before actually really encoding them into the book. So the initial scope of the library was to formalize large parts of the book on homotopy. You have a nice picture here, but I guess everyone knows the cover. And related mathematics, but it's now growing because people like the library and they're contributing things like the probabilistic computation that I talked about before, but other people have also been contributing stuff. So about the invariant foundation of mathematics, and I think this is an interesting thing to raise. One of the things that cannot be done, or at least is very difficult in higher order logic, is how to do abstract algebra or how to do category theory in those systems. So this may be something that we can discuss at some point. So for these topics, you would really like to have dependent types in universes. So we formalized large parts of the books and have an automatic tool that takes the book, looks at all the labels there, and generates generates labels so that we can encode the lemmas and point to the actual labels in the book. So this is also a way of seeing what exercises are still left open. This gives you some idea of the size of the library. So it's about 35,000 lines of code. Of course, this is just one measure, but it gives some feel for it. There's still a number of libraries building on top of this library that aren't included in this count. So I think the actual count is much higher by now. So it's the development is a test case for type classes, universe polymorphism, the use of proof terms in COC. So typically in COC you would be using tactics to do all your proofs, and here we're more using, of course, because we're in homotopy type theory, we actually care about proof terms. To see how to get automation to work, and also about, primarily about high reductive types. So how can we do this in COC, and how can we actually think about them in COC?
Question?
Yes.
So I don't know really whether I understand why you care more about proof terms because you're doing homotopy type theory. Could you try explaining?
Because you want to have the right proof terms, the coherence issues.
You care more about proof terms for the identity type.
Yes.
Than you do, like not in general, but for the path type.
Yes.
More things are proof relevant than in the type theory of the UIP.
That wouldn't stop you using tactics to construct those things, surely.
And as long as the tactics that you're using are constructing the right terms.
Like when you end up proving something about some path that you constructed, you do it with tactics, sometimes you'll get something that has more
The
like,
wrong path.
well, not the wrong, but more like tedious. So like you'll have, many associativities back and forth instead of the smallest sequence of associativities that gets you to the thing you want.
So the basics is it's based on Vladimir library. So we have the basic type formers and their identity types. So pi, sigma, w, universes, equivalences, and the n types. The n types are defined by the hybrid types, the truncated ones. We use equivalences, and we, of course, in the book, we're not. We discuss a number of possible ways to define the equivalences and then prove that they're all equivalent. I mean, there are a number of good ones, and now, of course, in the formalization, you need to choose one. So we choose to work with half-majority equivalences because they're convenient to work with. So you have two maps and that are inverse optical homotopy and one coherence condition. And the important thing about all these notions, and this is something that Vladimir has been stressing, is that this notion of equivalent is itself an H proposition. There's a big library of category theory building on top of our library. It's in a separate part. Well, it contains all the basic effects of category theory. Interestingly, there's also another library of category theory that was first done outside our HoTT library, but is currently being imported to HoTT and also on top of our library. So that it looks like we'll be having two in our library. We need to see how we're actually going to do it. So we're using a lot of COG features. Universe polymorphism is very important, and this is because we're not using resizing types. So we're actually trying to be honest about this cumulativity. And so a lot of constructions are polymorphic in COG. The problem is that inductives are not. So in also based on the
polymorphic, you mean you're talking about universe polymorphism?
Universe polymorphic, yes. So yes, COG has an infinite progression of cumulative universe, so this is different from lean. And a lot of the definitions are universe polymorphic. And there are good heuristics of putting things in the right place, in the right universe level. The problem is that these heuristics don't always work, and this requires a lot of extra work. And after discussing with Mathieu, we now have explicit annotations of these universe levels. So this is very convenient.
Didn't they have them to begin with?
They didn't have them to begin with.
Why not?
Because no one cared enough about them to actually. So usually things went well, but now we're actually pushing these things so that we actually need to handle them explicitly. There seems to be a solution for this now, because currently getting everything at the right universe level requires quite a lot of care, and also to do it right, COG is building up a large collection of constraints and then checks in the end that they can actually be satisfied. And that takes a lot of computational resources. There's a new implementation by Mathieu Cézot and Amin Timani on polymorphic universes. It has just been pushed to in the main prof branch something like last week. And this will solve a lot of our problems. So we need to go back and actually probably remove a lot of these annotations and hope that things will actually work. So this is one of the just finish one. So we hope that this actually solves a lot of the issues that we have.
Will this new feature allow to express the resizing rule as an axiom?
I don't think so. Why do you think it would?
I don't know, if you have access to like a kind of universe data structure,
yes,
you could hope that it could be internalized somehow and have some syntax to say, I want to have this resized.
Oh, you mean these annotations?
Yeah. Can I
I
have
don't
access
think
to how things are implemented? Inference and checking.
No, I don't think that's its problem.
Would be cool.
It's just the annotation that is so.
Okay.
COG is building as I said, a set of constraints, and you're now allowed to explicitly put these constraints. Yeah, maybe more can be exposed. I don't know.
Are you going to say something about some truncation.
Yes.
Okay.
So one of the nice things I think is that we can now have large power objects. For instance, the power set of the natural numbers would actually look like so. So you have so if you take a map to the propositions, it will end up in one higher universe. But this will, you don't need to actually, if you just write this, then it will actually unfold to something like this, but you don't need to write this explicitly. So you would,
Is that good? I'd say
sorry.
it's bad.
So often these things actually work very well. So often your heuristics work. And what I'd like to emphasize is that we can get a lot of predicativity by universe polymorphism. So you can write down the naive impredicative definitions, but actually cock under the hood will actually work for you and show that it actually works predicatively. So this I think is nice. And as a test, we proved, for instance, that empties are surjective. So the usual constructive proof of that is impredicative, but if you write down the usual constructive proof, it actually works. And of course, this is a strong case where you're actually using univalence or the propositional version of univalence to be more explicit. So this is, I think this is nice. So we can get a lot of predicativity by just using universe polymorphism. For the old people in here, we actually have an intuitionistic high order logic inside univalent foundations. I think that's nice. That's a way. This makes it easier to import IDs from high order logic into type 2, and that was something that was difficult before.
Sorry, me.
Yes.
In high order logic, I'm just thinking about it as church type theory.
Yes.
There is this type of individuals. How do you interpret it in
Type of individuals.
of individuals?
Usually it's just natural numbers.
Yeah.
I mean, in HL, it's usually theory with this directly introduced. You just want to have an infinite type and the natural numbers.
Yeah, thanks.
Because natural numbers normally defined in
I mean, you don't have data types or you define data types, or you construct data types out of your individuals.
okay, so you take map to be individual.
Yeah, I mean, you have individuals and then you cut out not, but in the end you can prove that individuals is essentially.
Yeah, by having maximum infinity.
Yeah.
Yes. So we're using a lot of type classes in search. So this gives you a way of doing logic programming at the meta level, and this is very close to the use of canonical structures in mass components, for instance. And there's now some slow work in actually combining these two implementations of type classes into something. So I'm really hoping that this support for this will become better. But for now, we're using the mass classes design. So this is a library I've built with collaborators, Robert Krebs and Elis van der Wegen. And this is a big library on algebraic structures, ordered structures, categorical structures. And it's now being integrated into the HoTT library by Gaetan Gilbert, who did an internship with me. But we're following this design of the unbundled structures. I won't go into technicalities here, but this allows you to do a lot of search and deriving the right. This is very convenient for searching, for instance, the right truncation levels. So you will hardly ever need to actually specify them. It will just automatically find them. You will also find features like this in the type classes are records. So this is something that came up before also for canonical structures. But we have proofs about the equalities of sigma types. So in some way you need to, there's no way of stating actual proofs about equalities of record types because there's no general syntax for them. So you need to first convert a record type. So this record type, the isograph is a record type, and it's a record type because you want to use type class search to automatically find out that something is an equivalence. But then if you want to prove something about the equality of equivalences. You want to have proof about sigma equality of sigma types. So you want to unfold this into a sigma type, and we have a number of tactics that actually handle this stuff. There's also data for records, and that's one reason why they're actually convenient. So this is why proof terms are important, because then you can write a slick proof of the Ekman-Hilton argument. So this proof, I think, is originally due to Steve Audi, and this actual cock proof has been written down by Mike Schulman. So this is just very short, and just by using the right proof terms, constructing the right proof terms before, the proof actually becomes very short. So this is concatenation of paths, and this is horizontal composition of two-dimensional paths. And this should be the inverse of the path. So you can see that you can actually write down very short proofs, and this is one place where the proof terms are actually very important. What would be very nice is to actually have better. Yeah, so we would like to have ACTA style support. Fortunately, there's work in this direction by Mathieu Souzeau and his team. And yeah, so there's progress there, but we're not there yet.
But that's not.
Sorry.
Well, your goal is not immediately pattern matchable here because it's about loops, right? I mean, it's not as if this would just be raffle.
No. So this is a general remark about yes.
Yeah.
This is a general remark about building proof terms, and we want to have better supporting.
Right. I'm just saying this particular example looks pretty much the same, even if you have that.
Yes.
Okay.
Thanks.
Yeah.
Ekman?
Yeah, so I was going to ask how that would play a role in this proof here.
Okay, thanks.
What is the colon greater in the statement?
Yeah, what is one?
One is the is REFL. And colon, you can do that.
Yes.
Yes?
Yeah, maybe explain the formulation of the theorem so
Yes.
we understand the syntax.
I don't think I have the time. We have five more minutes.
P and Q are paths between REFL, which is
Sorry to move on. So,
higher loops.
I mean, we've talked about higher inductive types before, but let me briefly say so. So inductive types allow you to freely generate terms, and higher inductive types allow you to freely generate equalities too, on top of terms. And we can encode spaces as objects freely generated from objects, paths, paths between paths, and so on. I mean, main examples are the interval and the circle. I mean, the most basic examples, but then you have many other constructions from algebraic topology, CW complexes, for instance. It looks like we can encode all of them. And many experiments from the book have actually been formalized in the library. Other thing is quotient inductive types. This combines the quotient types, as in the higher inductive types, with inductive types. So this is actually an even more complicated construction. The inductive types are now supported in an experimental version of COP by the induction recursion.
What are you doing to provide these things? Is my question actually.
That's
COC itself, right? Is just
that's
an inductive
yeah.
construction.
I'm getting there. I just wanted to motivate the So, but just to give you some more instances, so lots of examples from algebraic topology, the truncations, of course, but also a model of set theory, the commutative hierarchy, real numbers, both the Dedekind real numbers, the Cauchy real numbers, and the surreal numbers, surreal real numbers. So really many examples like this. We have short synthetic proofs in type theory. So synthetic proofs in, you all know this, I guess. So some examples: classifying spaces of automorphism groups, theory of idempotence, infinity groups with actions, and many more. So how do you do this in Coq? Well, you look behind you, and there's Dan sitting, who came up with this trick. So Dan used ACTA modules, and the Coq module systems are slightly different, but we were at the institute and we were talking to Yves Barteau, and he actually implemented something called private inductive types. So basically, we copied the features from ACTA to Coq.
But, I mean, the first time you did it, right? I mean, it turns out you can prove true equals false. And then you have to do something really arcane, and we hope that you still can't prove true equals false.
No,
We don't know, right?
So you can prove true equals false. That's
No. You know what I mean. I mean,
Outside.
I know nothing about the meta theory of private inductive types,
Yes.
right?
No,
I think they're private, right?
Yeah.
Maybe they are, maybe they aren't.
Yeah.
In ACTA,
Well,
it
it's
turns
just-
out that even though you didn't know the name of two
Yeah.
constructors,
Yeah.
you could tell they
Yes.
you could use their injectivity even if you didn't know their names. And you
Yes.
got the proof.
So
that true equals false in
So
bold.
currently there's no known attack at this on this approach, but there might be 0 days that we're not aware of.
Well, there might be, right? But I
Yeah.
mean, why not just
No, so-
why not just assert some things? Because
Well, this is the only way we can. Okay,
Wait,
why not just assert? This is because now we get induction principles that actually compute on point constructors. So that's that was the
you could
insight.
just assert those principles, right?
No, you cannot change the computation of Coq.
Well,
You don't get all the definitional equalities.
You don't get the definition. So, but yeah, I very much agree that this is just a hack, and just to allow us to continue to experiment with these things. But yeah, there are very few guarantees about this.
I mean, I think the right solution would be to implement some mechanism for higher inductive types in Coq,
Yeah.
and then you would trust that. This is
Well, probably,
semi-user.
yeah,
that's right.
probably even better. We want to have some kind of cubicle version in Coq or like that.
Okay, so this is like a semi-user level way to do that.
Yeah. Then there's a large library on modalities. So modalities are idempotent monads, and they generalize truncation, some proof and program transformations like the A translation, CBS translation, and Lovier-Cheney topologies from topos theory. With Egbert and Mike, we recently put an article on the archive, and many constructions have been formalized by Schulman. And the interesting thing here is that this makes very heavy use of modules, and this is essential because we need record types, but allowing each field to be individually polymorphic. And this cannot be done in a standard way. So this is maybe a hack, but in any case, there's something to be understood here, because the standard way of doing this in Coq, these modalities or reflective subuniverses, cannot be done in Coq. So there's actually something going on.
So you essentially have a quantification of a universe inside of your record.
Yes.
Okay.
It may be possible to do this in ACTA, because ACTA has a universe that's higher up than all the other universes. ACTA knows
But you can't access it.
So it's,
For some things you do.
so it's, as I said, so there was a suggestion that maybe this could be done in ACTA, but I haven't thought deeply enough about
I mean, I don't have access to set omega.
No, but for instance, you can have a hypothetical univalence axiom that works for all universes when a quantification of the levels.
We have a record that has
Yes.
for all I would have.
There's a thesis by Kevin Quirin, who builds on number of libraries and also develops some theory about modalities. So the consistency. So there's a question. So we're using Coq, but disabling some features and adding some new ones. So are we still consistent? Well, one important disclaimer is it's not known that Coq itself is consistent. So this is something that we need to keep in mind. So what do we need to trust? Coq's kernel, the axioms, universe polymorphic modules, if we want to have the modalities, and the implementation of private inductive types. These axioms are semantically verified by the simplicial model, and for Hitch we now have the paper by Peter and by Schulman. Yep. very much going on. Our development encourages and inspires improvements in the implementation. So we're developing new features and running into problems and then discussing with the Coq developers, and then new features are added to Coq. So I think this is a nice way of working. So we have very close collaboration with Mathieu Sousseau, and there are a number of features that were added to the Coq library. So this indices method that was added before, also for the Unimount library, and we've completely removed the standard library and put things back because the standard library actually depends on prop and we cannot use it. And that's irritating because the tactics are actually, so this is also a flaw in the design of Coq, because the tactics actually depend on the standard library, and they're trying to remove this now. So trying to reorganize the code so it's better supported. And private and victim types. We do a lot of software engineering, so we use GitHub for code review, 2 pairs of eyes, so before something gets allowed. We have an extensive style guide. We use Coq documentation, Pluviola, so that you can actually replay proofs by mousing over, so you can actually see the proofs and see what's happening in the proofs without ever needing to install anything. There's also a JavaScript version of Coq where you can run our stuff directly, so there's no need to install anything. You can run it on the web. We're using Travis to do continuous integration and timing, package managing, Emacs, proof general, tags, company Coq. So all of this is supported and makes it easy for people to use it. Related work, of course, you've already seen a lot in the past hour. They use type in type, and we use universal polymorphism, so that I think that's a trade-off. There's interesting work. There's small basis for HoTT that builds co-inductive types from the natural numbers and resizing based on our HoTT library. The resizing axiom that they're actually using is the one that's semantically justified, and the same one is in the book. So that's the one you can actually state inside HoTT as opposed to using type in type.
That's what. Sorry, that's what we call weak resizing rule.
The weak resizing, yes. So every proposition is equivalent to 1 in the lowest universe, as opposed to being equal to, or being itself indeed equal to 1. There's a lot of projects building on HoTT. Someone is developing an SQL for semantics of SQL databases, and this is becoming quite a popular project. 2 libraries of category theory, the probabilistic programming that I've talked about before. Of course, we're going to hear more about these projects later on. I'm also involved in guided cubical type theory, so towards adding co-inductives to HoTT and also applications of HoTT to programming verification. So this is what I tried to say. So higher inductive types, universal polymorphism, a basis for other formalizations, a testing ground for new Coq features, and a foundation for experimentation and formalizing with new ideas.
Thank you.
So how do you position yourself towards Unimath? I mean, you like fierce competitors or importing ideas from each other or converging eventually?
It would be nice to converge eventually. So the main...
They're like the delinquent brother safe sister.
So the main difference is the experimentation with higher inductive types. That's really the big difference. And we also like to stay predictive as opposed to the Unimount. We're trying to use we're trying to use the Coq features that we're used to before, so all the automation and so on. We're just trying to build the best library we can do from a software engineering point of view. So we're not trying to be as minimal as possible. On the other hand, we're not using type and type, we're not using any resizing rules. So in that sense, we're also more conservative. But yeah, one of the interesting things actually I mean, this is a very good question. So is there a way to actually automatically translate between the two or actually link them up. And this, of course, is more generally, I mean, all the work that's also been done in Agda and in Lean. So can we profit from each other, apart from just looking at each other's code and copying the statements? It would be really nice if we could do it better.
Well, it's likely one can translate Unimass into what? I mean, mechanically.
Apart from the type and type.
Well, resizing rules can be replaced. All the users which we have can be replaced easily by having
By having?
by hiring active types.
Hiring active types, yes.
Well, but maybe. Well,
And the resizing rules.
except for the set of subsets, which is not which is going to become predicative. But as you
Yes.
said, the vocal universe automation takes care of predicativity.
Yes, well, hopefully the new version.
I mean, hopefully we never have kind of loops
Yes.
in that sense. So I would say that there is a good chance to be able to mechanically translate at least big chunks of Unimass into what. I doubt about the reverse.
About the regulars. Well, everything that's done with hierarchical types, this cannot be translated. But there's no way that can do it.
I mean,
Yeah, so-
they're experimental. We try to be kind of to become a sort of a real working horse environment.
Apart from the big leap of faith that one needs to do by using type and type.
By using resizing rules,
Yes.
Thanks again, Bas.
And the resizing rules.
Maybe we'll have a 5 minutes break.
No,
For the next
that's the
session.
problem.
So we'll start again at, let's 40.
Yeah. So how do you tell where you're using the
It's, in practice, it's not even in the
Oh, okay.
because, I mean, we don't really trace it. But we use no more than 3 universes. The idea is that the human mind will
Okay. Yeah. Yeah. It'd be nice if there was an automated way to see where it was being used.
I mean, each place from where you can trace point.
But that's good.
Yeah, I think 3 is enough.
Benefit from having all the different ones? Should they compete with each other like racehorses to make?
And
Yeah, so when you can sort of think about it.
Training against each other?
Well,
I think.
If you want, originally want to do it.
there is another example which they want from here. Which would say that that can actually be
Also, cubicle
for which there exists an equivalence with T.
So,
Is again a new one.
Saying that you closed on the one forming the
Yes, but if you take as an action,
They're both from CMU.
Well, you don't have that.
we don't have an abstract at the moment. But it would be good to have it because then we can really build
because it's
things.
not quite. Okay. You want that?
Of building things with high level.
Oh, you're doing that now.
So he's, I said, 12:45?
Because
Yeah.
good.
Yeah.
reciting rules in a form that say you're in your field of university. As I understand by reciting rules saying, if you have two cumulative universes, you have a type in the lower one, and a type in the higher one, and an equivalent between them. Then that tells you that there is some type in the lower universe whose inclusion into the upper universe is judgmentally. Yes. So I don't know. I mean, this is something that scares me a little bit. It doesn't feel obvious to me. Well, it doesn't feel obvious because you don't have a model. Right, but I mean, there are some things. Let's say, I also slightly worried about the model that Devlin does. But I'm not scared by them. I feel confident that the deadline they will be. This.
Yeah, we don't know whether it's true or not.
I would put a moderate.
It's kind of create some, you know, some sort of like what do I say? Excitement, yeah. What is the word?
I would based on inductive. I would put money on this. I wouldn't walk on a bridge.
Set up a whole system for cash awards.
Okay.
What about size?
But it's also, doing it is also a challenge. Try to create a prediction. And that is a very healthy thing for.
Yes.
Yeah, I mean, because that actually proves the
There's a model there.
When Martin Luther published his first paper, then
So the next talk will be by Floris van Doorn, and he will also talk about the hot library, but this time in the lean proof system.
Thank you. Yes, I'll try to be quick because we're a bit behind on schedule, but I'll talk about the hot library in Lean. So we've already had a talk by Jeremy on Lean, and there will be more talks on Lean next week. So I will go very quickly over what Lean is and focus more on the library. But so Lean is an interactive peer improver, which was announced in 2015, and it's developed by Leo Demura and Microsoft Research. And it's open source and available on GitHub. So there are currently two versions of Lean in use. The newest version, Lean 3, doesn't support HoTT type theory yet, and there are currently no plans to support it, so who knows what's in the future. But so there is a stable version, Lean 2, where we already developed the hot library before, and so we are continuing to work in Lean 2 to develop the library there. So some of the features of Lean include that it implements dependent type theory. It's written in C++ and has multi-core support for parallel checking of proofs. There's a very small kernel, and there to illustrate that there are multiple independent type checkers just written by PhD students as just a side project. So that's practically possible to just to write your own kernel. The type theory. So there are standard and hot instantiations. So we'll talk about the hot instantiation. There's a very powerful elaborator in Lean. You can write proofs using terms or using tactic modes. There's a very nice Emacs mode which checks your proofs on the fly, and there's also a browser version which runs in JavaScript. So the kernel implements the following things. It implements a hierarchy of universes indexed over like an external natural numbers, and they are non-cumulative. So if you have a type in some universe, it doesn't automatically also live in higher universes, opposed to Coq. So that solves some of the problems with Russell universes, because because you don't have cumulativity. So
But I'm sorry, but is there a standard function from one to another?
yeah, they're in inductive functions. So inductive types, you can declare them in higher functions than necessary. And so there's a lift function which goes from any universe to any higher universe. And you can prove that's an equivalence and everything. Or sorry, you can prove that the lift type is equivalent to the original type. So there's universe polymorphism, which we heavily use so that you can define functions in all universes simultaneously. There are dependent products with the usual ADA rules, and there are inductive types. It's it's much smaller than, for example, in Coq and ECTA, because inductive types only generate the induction principles and the constructors and so on. In the computation rules, there's no pattern matching or something like that. And so to give an estimate of the size of the kernel, so there are reference type checkers, which are about 1,500 to 2,000 lines. So some things the kernel does not have are things like a termination checker, fixed point operators. There's no pattern matching in the kernel. There are no co-inductive types, no inductive or inductive recursive types, no universe connectivity, and no ADA rule for records. So the kernel is really, we try to make it lean. Yes. Well, for example, the ADA rule for records, I would actually wish we had it, but it's quite easy to work around it. So in addition to the kernel, we add two things to the HoTT library which you also need to trust. So we add the univalence axiom just as an axiom, and then we add higher inductive types, and I think any bits will like our approach very much, namely we just postulate the higher inductive types. So we postulate the constructors and the type formers of the quotient of two higher inductive types, quotients and truncations, where this is the specification for the quotient. And we also postulate the induction principle, and then we add the computation rule of the induction principle as a kernel extension.
When you say kernel extension, what does that mean?
So the lean kernel supports like a way that you add new definitional equalities in your and we add two of them for the induction principle for the quotient and the induction principle.
Is that like a rewriting ACTA?
I think it's very similar to the rewriting of ACTA. And so yeah, so when I say quotient, this is the type which I mean. It's also called a colimit of a graph, or sometimes typal quotient, where typal is the adjective of type in contrast to set quotient. So you have a type, and you have a family from A to type, and so it's you get points from A, and you get for any if you have if x is related to y, then you get a path from yx to y. So the identity type in the quotient is freely generated by the relation R. And so we don't use any type and type or resizing rules. So the semantics should be quite tractable. Like I think simplicial types and simplicial sets and cubical sets should both model lean. I think there's still some open issues with that. Quotients have like large elimination. This is not a proof or a conjecture.
Sorry, can I ask a question? So, that's an actual piece of syntax in?
No, this is not. This is only the specification. This is not actual syntax.
Oh.
We unfortunately also
You got my hopes up.
Don't have higher inductive types. And what we use in lean is that we construct from quotients a lot of other higher inductive types. We cannot construct them all, but we can construct a lot of them which are used in practice. So for example, we construct a push out, and then we get also the suspension, smash, join, spheres, and so on. We can construct sequential co-limits. We can construct high inductive types with two-path constructors, such as the torus and Eilenberg-MacLane spaces. So there's a construction of the propositional truncation, and then Egbert has a construction of all the n truncations, unfortunately not yet formalized. So if this would be formalized, we could even decide to remove n truncations from the kernel and only have quotients, and even more general localizations. These can all be constructed from just quotients. So on top of the kernel, there's an elaborator which figures out all the implicit information. So it figures out implicit universe levels. So you can write universe levels explicitly, but most of the times you don't have to. There's first order unification and higher order unification. It does computational reductions, overloading, coercions, type class inference, definitions by pattern matching, and tactic proofs. So a lot of the features which you want and expect. A theorem and a proof assistant. So this is, for example, some of the pattern matching Lean can do. So it can do dependent pattern matching like this on vectors. So for example, in this example, we define the tail of a vector and we only have to do one case. And the nil case is automatically discarded. Well, solved by Lean. It's discovered by Lean that is not necessary because you say that the vector is a positive thing.
May I ask a question about this index? So, what is the difference between the end of the lines, this and the last one? Like you don't have a period like in code.
Yeah, so there's no period to distinguish when a proof is ended. So a proof ends basically when you write, like when you have a new definition or something that marks the end of this.
Oh, kind of the beginning of the next one is
yeah. So if I continue writing on this line, then it would be treated as T applied to whatever is on the next line.
Where will Lean is not like Haskell, is it? I mean, it's not sensitive to two-dimensional layout.
No, it's not sensitive.
It's more ML in Haskell.
Oh, and what I should mention here is that all these pattern matching notations are then compiled down to recursive because the kernel only knows recursive. So this is all compiled down to applications of just recursive. So this is another feature of Lean. You can do nice calculational proofs. So this is an example. If you have a type and two families over that type, then the sigma types commute. And there's a nice calculational proof where you write the left hand side is equivalent to this, is equivalent to this, is equivalent to this, and then here are the proofs of why those steps are valid. And then, for example, there's an example tactic proof. I'm not expecting you to read this, but so for example, this is the dependent universal quantity of the circle. So this defines just a function. If you have so you have a family over the circle, and if you have a point over the base, and you have a dependent path over loop, then you get a function out of the circle. And one nice thing what you can do is we do introduce a variable of the circle, and we can use the induction tactic. Also, the induction tactic we can configure it so that it also works for induction of higher inductive types. And it will recognize by itself if it has to do dependent induction or non-dependent induction. So then the HoTT library. So it's separated into two repositories. The HoTT library, which comes with the Lean 2 itself, and then there's a spectral repository where we are working more like that's more for the in progress formalizations, which are still very much changing every day. And then if something is stable in the spectral repository, we move it to the HoTT library itself. So they are sort of there's no big distinction between them. Eventually, we'll probably move most things from the spectral repository to the HoTT library. So the main goal of the HoTT library is to explore and formalize synthetic homotopy theory. There are also some other goals. We've done some category theory. We've done some experimentation with higher inductive types, mostly reducing higher inductive types to quotients. And this is an example. This is the count of the lines of code. So in pure code, it's like 33,000 lines in the HoTT library and 11,000 lines in the spectral repository. And there are many contributors. Jacob from Romer, Ulrich, and then a couple of people who are here, Jeremy, Egbert, Steve, and Mike has contributed, and many others. I can list all here. So these are some of the things which are of synthetic homotopy which we've formalized in Lean. We formalized almost everything of chapter 8, the synthetic homotopy theory chapter of the HoTT book. So that includes the Ferdital suspension theorem, Whitehead's theorem, the Seibert-von-Kampen theorem, long-stack sequence of homotopy groups, the complex and quaternionic HoTT federations. We've computed homotopy groups of spheres, and then there are things which are not in the book, like the adjunction between the smash product and pointed maps, cohomology theory, and the Serre spectral sequence, which is almost done. And then there are work in progress about spectra and homology theory. Also,
sorry, for the spectral sequence, you probably need something like double complexes.
no, we don't. It works for any type. The Serre spectral, yeah, the Serre spectral sequence works for any type. And so this is a rough estimate. The things I've highlighted is a rough estimate of things which are only formalized in Lean, where there should be an asterisk here. So there have been different formalizations of the long-stack sequence of homotopy groups, but I think our formalization is the only one where you can get conclusions of the actions of maps on end homotopy groups directly. And then the quaternionic HoTT federation is only formalized in Lean. I think the computation of pi3 of S2 is only formalized in Lean. And then the smash pointed maps adjunction and the Serre spectral sequence are also not anywhere else. So this is the long-stack sequence, the statement of the long-stack sequence of homotopy groups. So if you have a pointed map from X to Y, so that's a map which preserves the base point of X. So it sets the base point of X to the base point of Y. And then you get a long-stack sequence of homotopy groups of this, which relates the homotopy groups of the space of Y, the space of X, and the space of the fiber of F. And then you also have the horizontal maps. You can compute exactly what they are, and diagonal maps are given in the proof.
I have vibration sequences quite advanced in foundations. From where it doesn't seem to be very far to here.
My experience was that the translation, so getting from vibration sequences to here is actually the largest part of the work. That is my experience in formalizing this proof.
The vibration sequences give you the periodicity.
Yeah,
I mean,
so the vibration sequences gives you this sequence, but then you have to prove that it's actually equivalent to that sequence, and that is actually quite challenging, and that the maps are correct also.
Well, that's probably equivalent to describing what are the maps in the derived vibration sequences between the spaces themselves, which is something which is in my proof. But
okay. So this is another example. So this is work by Egbert and Ulrich, formalized by Ulrich, which about the HoTT vibration. So it assumes that you have a type, an H space on A, and A is path connected, and then you can define a HoTT map from the suspension of A, the family over the suspension of A, and then the total space of that is a join of A with itself, and then there's an H space structure on the circle, which gives you the complex HoTT vibration, and an H space structure on the free sphere, which gives you the quaternionic HoTT vibration. So here's the statement of the adjunction between the smash and the pointed maps. So it says that this PP map is the pointed type of pointed maps from between two types. So it says that pointed maps from the smash product to any other type is equivalent in a pointed way to pointed maps from B to pointed maps from A to C. I could have swapped the A and the B. This is the statement, and from that you can, for example, derive the associativity of the smash and the naturality of that associativity. This equivalence is also natural, which is not so let me skip the item, this about isometric plane spaces. So this is the statement of the Serre spectral sequence. So here is a statement in words, and this is a slightly more general way how we formalized it. So the Serre spectral sequence says that if you have a simply connected pointed type X with weight X naught and a family over X and a group G, then then there's this arrow, and then there's a group here which is the cohomology group of the total space of F with coefficients in G. I don't want to go into the exact definition of cohomology group, but it's some algebraic property of any space. This is the cohomology group of X with coefficients in another cohomology group, namely the cohomology group of the fiber in G. And this arrow means that in some technical way, this type, or this should be sigma, the total space of F is Z, so that this cohomology group is in some technical way built up from these cohomology groups. And this is the statement in Lean, which is a parameterized version of that. So I want to do one small extra on pointed maps. This is like a design, more design, how to design a library than about the hot library, specific to the hot library. But so a pointed map from A to B is just a map which respects the base point. If you build enough libraries, enough of the library, you will realize that at some point you will need to generalize this to dependent pointed maps. So a point dependent map is a dependent map which respects the base point. And actually here in this formulation you notice that you don't assume that B is a pointed type everywhere, only over the base point A. So you can even generalize this slightly further to say that you have a pointed type and just a type family over it and only a point in the base point. And then you can define a dependent pointed map, like a pointed map which you share to base point like this. And so what this gives you is, that you can define these two as special cases of this. And one thing this gives you is that you can define a pointed homotopy between two pointed maps. So if you have two pointed maps F and G, which can be either of those, so let's say this because that's the most general, that is an element of a dependent, so it's a dependent pointed map from A to equality, so from equalities from FA to GA, because this makes sense because we have a base point over the fiber, namely there's a point in here which is just a concatenation of the facts that F and G respect the base point. And this is very nice. For example, you can define two homotopy, so a homotopy between homotopys as just again a pointed homotopy. So this is kind of an engineering solution to reduce the amount of different concepts in pointed types. You only need pointed dependent maps, basically. As a conclusion, so some of the, I will, as a conclusion, list some of the advantages and disadvantages of Lean. So Lean has very powerful unification, which allows you to make higher order arguments implicit. So when you have a transport or dependent path, most of the time don't have to write the family over which you transport. It has a very small kernel, and it has a large library for synthetic homotopy theory, and it's also very fast because it's it's written in C++ and has multi-core support, and there's a lot of effort done in the performance. So the type checking is quick. So some of the disadvantages is that powerful unification actually also has a problem, namely when you write a term which is type incorrect, then the lean elaborator will look through all kinds of possibilities to figure out what you mean, and then at some point it will know that all the possibilities failed, and then it will give you an error message which sometimes does not have anything to do with the place where the actual error is. So that's kind of annoying. So the powerful unification degrades the error messages. There's no active development to the source code because we're working in the Lean 2 branch. And one problem is that so to simplify the goal, just to show the goal in a convenient way is sometimes hard to do. So it would be nice to have better tools for that. Thanks for your attention.
Thank you.
So on your last slide of the disadvantages,
Yeah.
at least the first two, it seems, are ones which would both be solved by upgrading to Lean 3, etc.
Yes.
Would the third one also?
Yeah, I think so. So Lean 3 has a lot of tools to support your own automation and so on. So you can write like a definitional reducer which just does some definitional reduction to your goal, and then to simplify your goal. And I think since you have a lot of control over what it does, I think that would solve the third problem as well.
And what is the problem to put in library to Lean 3?
Nobody has offered to do it.
I mean, there's
I'm
no
not
hot support
able.
in Lean 3 itself.
Yeah, so there's no hot support in Lean 3.
Why is it not?
So the developer is under a lot of pressure to just deliver a product for the standard mode for program verification and things like at Microsoft Research, and he didn't have time to maintain also hot support.
Also, I mean, one reason he also said it's apparently not so clear what you actually want to have in hot, as far as I understand. So, should he directly implement cubicle hot already, or should he go first with usual hot and later? Is it required to extend it?
Yeah, one of his arguments is also he doesn't want to spend effort to support hot, so to just support like the hot in the way it's done in the book, because his argument is that what we HoTT factories really want is a cubicle system with, and so he doesn't want to spend effort in a system which is not optimal.
So how long would it take to actually implement cubicle in Lean?
I think you should ask people who have experience.
I mean, there's an implementation in Agda now, so
I don't know, yeah. I think just changing the kernel and maybe elaborator might be feasible, but there are a lot of things to help the automation and so on top of it, which might be hard.
Yeah, and one other question. I asked Dan this already yesterday. So these things like spectral sequence and so forth, they, if I understand correctly, were originally developed to solve problems in number theory, maybe, or maybe also analysis. So anyway, my question would be whether it would be possible to sort of instantiate the synthetic homotopy theory with those, example instances for which these concepts have originally been used, and then maybe get new or more modular proofs of classical results.
So I do not know of applications of spectral sequence to number theory, but they are very powerful too in homotopy theory to, for example, compute homotopy groups of spheres or give properties.
And then those.
Yeah, so we are, if you finish the construction, then we really want to work on the application.
Time for a last quick question.
Well, I have a last question to Peter. How far is how close we are to having a model of the entire inductive type of the skill?
That I don't know. I don't know how the Lean one does it.
No, I'm not asking about how Lean does it. I'm asking whether you can model it in some.
So just the quotient higher inductive type.
Lean
Yeah.
just has homotopic push-ups.
So-
It's just homotopic push-ups.
Right. So in so what Mike Shulman's and my semantics gives in suitable model categories, which in particular includes some visual sets, it gives that construction, but there's a size blow up, so the universe isn't closed under it with that approach. So you have that construction sort of globally, given two types you have thing, but it lives in a larger universe than they did. There is a trick that Andrew Swan has suggested, which I think might well be able to solve the size blow up, but that hasn't been worked out carefully. So I think that's where it stands. It's done with a size blow up, hopeful that it can be adapted by ideas of Andrew Swan to get a universe closed under it.
What about in the cubical sets? I suppose.
So I think,
Some hits, isn't it?
yep. So there, I think I'm not the person to answer on that, but there I think it's actually a bit less problematic because the primary placement can be taken in a more uniform way. Is there someone here who is a cubical person and can answer that?
Or maybe we can postpone the answer and thank Lars again. Hello, last speaker from Estonia about yet another library about homotopic type theory, but this time in Iceland.
Alright, so I think I only have 15 minutes. So let's be fast. Oh, what? Oh, also I'm hungry. Okay, so anyway, so you won't be too long if you're hungry, so I'm with you. So let's introduce this. So like years ago I was at IS and I also at CMU like learning the hard stuff. And at that point of time, only the Kalk and Egg only the Kalk and Egg are the proofs are ready to use immediately, and I want to do experiments. So for some random process, randomized process, I pick Egg. So our goal is to, and my goal is to experiment some of the things I learned, how to put them into code and in Egg.to type check, try to type check it at least. And then, of course, like for example, when you're trying to do that, then you also have to prove lots of other theories. Like, at one point I want to do a little bit of cohomology theory, and I need to do a little bit group theory in order to finish that. So this is the goal, but in the middle process, we also prove lots of other things. So that's basically how the library is structured. Next page. So the one thing I want to emphasize is that it's really decentralized. So yes, there's a big one there that is under the hot group that are half reflectory, but there are also all sorts of forks or like older versions of experiments. For example, the experiment I did was actually under my account, then I abandoned that and I joined Guillaume to do another thing. We copy each other's code very frequently, and we also and it's not even forming a DAG. Like there's a lot of circle. I copy yours and you copy mine, and we're all cool with that. So anyway, the coding theorems and forking are very common. And we're also trying to, for example, I think, oh, it's not this year. I think there's one ECTA development I really want to merge into the first one. The first one is the main one, so if you want to have some thing for reference, I think you can consult the first one, but there are also all sorts of other things that I don't even know of. All right, so this is I think one core part of the ECTA that you can really just create your own part. But since I'm not the authors of all this, so I will have to just focus on one particular one. And even with that particular one, I'm only contributing to a portion of it. So I'm not going to really introduce to you the entire picture, like what exactly has been done there. But I can list lots of them. So we have recommendations. I'm now working on a generalized version where the truncation is replaced by some locality condition. Of course, I don't have time to, oh, it's only 5 minutes. Okay, so we have the total space of the half vibration, and also the 3x3 lemma, which is basically a coherent condition about a push-out that can be used to prove the half total space of a half vibration. That's why I listed in the same law. And there's also a Van Kempen theorem. There's also something in the cohomology theory about the Victoria's sequence basically from the axioms. You can prove that there's a sequence. There's also a cubical reasoning that so you have identified, but often when you are trying to code it out, you realize you actually want a square. You want to talk about square directly. Even though you don't have even though you are not using cubical type theory. Now, for a long time ago, we know that all the cubical structures are so wonderful. So I think this is mainly done by Descartes and Guillaume, Dan and Guillaume there. And also have Fontenau. It could be this is actually a correlation of the spatialized version of the recurrency, but we also have the different code for that. And we have elegant mapping spaces and so on and so on. So there are just so many things. So these are the authors that people have contributed to the ECTA HoTT. I want to point out that I think Mike Shulman is the only person who contributed to all. Except including Unimas maybe? I don't know.
Including Unimas, yeah.
I don't know about Unimas, no? I mean, I don't know of any traces of it. Maybe there was something back.
Oh yeah, I still have to write some code to achieve this.
Completion. Wasn't he in the rest completion thing? Rest completion.
He didn't write any code, but he contributed proof.
Okay, so this is just fun stuff. Okay. So there are lots of things like going on here, and also proof of, as I said, all the other things are needed in order to show these results. But I won't have time to go into any detail of this, so I'll just talk about like what kind of features we are using. So ECTA, roughly speaking, is a multi-level type theory style logic or programming language, depending on how you view it. And it also has lots of crazy things, like inductive, recursive types, or very complicated mutual definition. They are all fine, right? As long as you can complete ECTA. And it has syntactically, so this is not directly about the proof strength of the type theory, but it also makes differences for ECTA from other proof systems, which is a powerful max parser. I can probably show you part of it in the end if I have time. And there's a pattern matching, and there's a very powerful dependent matching. I've seen so many camps that, they have implemented the ECTA style dependent pattern matching. But when I look at it, none of them so far, I think, are as powerful as the one in ECTA right now. ECTA has so many weird stuff that, I don't really have time to go into. And we also have the universal polymorphism. This version, the ECTA the one in ECTA is actually the second order polymorphism. Now, not only that you can have a quantifier talking about the whole universe, but you can also pass around something that is universe polymorphic. So this is, I don't think this is really well understood, but they put it in anyway. Yeah, so this is the spirit that, okay, I'll have a slide for this. So for automation that people might care about, we only have unification. I think in some regard, you can regard it as of some kind of automation. And we have a little bit of literal overloading, like the one to be treated as an integer and the natural number, and also the homotopy level or truncation level. And we have very few tactics. It really depends on your definition. According to some definition, this is actually none. But okay, I don't want to really go to a detail. Basically, you can pretend that there's no techniques. All right. So the high inductive type that has been a heated topic. So we were using dense streak that the Bas has talked about in similar to Kaggle, you have a private data type. But then in ECTA, probably has too many features and the pattern matching is too powerful. It's really difficult to prevent other people from proving false, or true equal to false, 0 equal to 1. There's a very lengthy document written by Guillaume saying that you have to apply this trick, you have to kind of define it in the private way, and then have another data type which take the element as a construction, and then have another one which construction just take a function from unit to unit. And all of this to prevent also weird usage of the pattern matching. I think in the end you need to apply 3 very messy hacks to prevent all known attacks, and we're still not able to prove it's correct. So I think this is the most civilized version. Let me just show you. So this will be the only ECTA code that you will show in my talk. I hope we can kind of go through it. So then right now, the definition. Well, let me do a disclaimer. This is a real ECTA code that will just run. But we are not using it right now because right now the circle is defined as a suspensional bool, if you know what it is. But I think this is still a very good example that I want to go through. You can define circle this way, just that we are not doing that right now. So circle is all postulated. I postulated that there's something called circle. And I postulated that the base is inside that, and there's a path between them. So from the base to base. And then I want to define the animation rule. Basically, that given these inputs, now if you know how to do with the base and you know how to do with the loop, and you say that you postulate that there is an elimination function. This is the eliminator from the circle to the theorem you're trying to prove. And then, but we want to also compute points. So this is the thing I'm talking about, the new feature we are relying on. You can postulate that, okay, there's a reduction rule for base. And so this line is really to hook this reduction rule into the ECTA. Saying now whenever you see this, F applied to base, you should reduce it to base, right? The proof that you put in. And also still have to postulate that this proof is that. Right now, the current ECTA kernel, you can also phrase it as a reduction rule and hook the rule into an ECTA so that it will compute base and proof. But we are not doing that because I don't think it's really well understood yet, and also the hardbook version only has the definitional behavior on the base, but being only homotopy on the loop. So we are using this version. So we are kind of, in some sense, very conservative, but in some sense also very exploratory, trying different things. So idea basically is to use this new feature to achieve the same effect of the dense streak without those hacks. Those hacks are really appalling in my opinion. All right, so this is how we do the high inductive test right now. Okay, so this is really the point I want to bring up, because I think this might determine whether you want to use Excel or not. It's not well understood that how the entire language is working. We don't really have any sort of like good consistent guarantee that, because a good consistent guarantee will be like maybe there's a core language and you can prove that as long as you believe some very large ordinal number and ordinal, then you can prove that it's consistent or something like that. But in ADA, it's not even clear what kind of core language is, and not to mention the theorem. Anyway, it's not well understood. Many individual features have improved. For example, that we have a without K, and you can isolate a part of the ACTA, and then you can prove that the unification algorithm is fine. But then it's then coded in Haskell, and no one has really didn't go through very rigorous auditing process or something like Tom did that using an unproof system to prove the correct unproof system and then make the data. So none of them has been done. So personally, I don't really trust the kernel. I trust ACTA proofs, but not the kernel. I trust that if you're using it in good faith, then the proof should survive. For example, actually I have this example. So there's a naive set theory. So we can prove something in terms of a naive set theory. And then people then realize that there's a paradox. But nonetheless, I think most proof in the naive set theory is still fine. So that's basically my model usage in terms of ACTA. I don't really trust the kernel, but I believe the proofs. So the model usage here is really highly dependent, and we really like to explore things. And you can see that every month there are some new features or trying to get more computational behavior and so on into ACTA. All right. So let me show you some statistics. So right now the structure is that we divide the ACTA HoTT library into two parts. So one is the core part and one is the interesting part. But the division is arbitrary, but we try to make it reasonable. So for example, the definition of a circle will be in the core, but the brackets messy will be in the theory. I don't think it belongs to a code. Anyway, okay, so we also have the same mechanism as a cloud that we use in Travis to continuous integration. What it means is that whenever you push something on GitHub, then there's an independent server running the ACTA and checking everything. So we want to make sure that no one is destroying the correctness of proof. And the thing is that it can be checked at least on this server 20 to 30 minutes. There's a wide range. Don't ask me why, because I just look at the time, the number of minutes that it needs on traffic is not a constant. So that's the best I can do. So yeah, there are some statistics about the lines of code. Actually, the tool I use doesn't recognize ACTA. I have to say that pretend ACTA is Haskell or something like that. So the numbers are down by pretending ACTA is Haskell. Yes, I think this is the last page. Yes. Oh, okay. So any question?
Thank you. Everyone's hungry.
So why do you have this decentralized model?
I think if people just want their own repository for many reasons. Some reason I heard of is that they want to do something and they really want to change the code library, but they also don't want to pollute the main one, the ACTA, while they are doing something else. And then so there's a fork.
So how many time do you spend on porting from one library to the other?
I actually didn't do much porting from other libraries. I did a little bit, but not much. Sometimes I did pull something from Ning, but that is more like understanding it and recording again. I did indeed some porting from the older version of library to the newer version of library. For example, actually I proved record message twice, config space twice, or maybe 3 times maybe. So the rewriting is interesting. We rewrote the entire library to use cubical reasoning. So you have a path over path and so on. Does that answer your question?
Yes.
One question. What in this library couldn't be done, for instance, in Lean HoTT?
I think it can also be done. That's why we are copying each other code all the time. Shows that in principle, yes.
But maybe something you would say it's more elegantly done in Agda or in Lean, or I don't know. Would you be able to
Because I can
compare
use
the
all
ergonomy
these.
of the systems?
Let me think. So personally, I can use all of these systems. So if you want me to code that, I can also do that.
And that's why I ask you: is there any feature of Agda or of Lean that you lack?
Which one gives more readable proofs
Yeah, for
for
instance.
mathematicians?
Oh, for mathematician.
Yeah.
I'm not able really to say I'm a computer science and any code is fine. In the syntactical whatever, like, as long as you can write down as a string, I can pass it.
So for instance, both Lean and the HoTT library use some sophisticated type inference, for instance with type classes like mechanism, and as far as I understand, you don't have this in Agda.
You could have that. We are not using it.
Okay.
So Agda supports a limited form of the type classes.
But do you think it's a good thing not to have them, or it's useful and you have them?
Having them, so mechanization, in my opinion, is a balance of like 3 factors. Like it's a machine time, the type checking time, user time, that how much code I have to writing, and the strength of the mathematical theorem. So I don't think there's a perfect solution. I think you have to sacrifice the other two to achieve that. You have to, for example, the type classes, if you're abusing it, if you put a type class everywhere, I think one version of the law library is trying to use the type classes, or what is called instant argument in Agda, to find the natural homotopy level, or natural truncation level. For example, when I say circle, I should already know that it's the level 1 or something. So you can use that, but if you use it too much, then Agda will be slower, because whenever you see that, oh, how should I find the proof of this truncation level, you have to go through all the possible proofs that are available at that, in that context, and to try to figure out whether there's a way to make a proof. And that could make a type checking slower. Does that answer your question?
I think the best predictor of what proof assistant was used for something is just who wrote it.
Oh, I'm not using about the best proof assistant.
No, the best predictor of like for Agda versus
for
Lean.
this spectral application.
Yeah.
Yeah.
But
Is there some identified feature of one or the other proof assistant?
Well, I think
Well,
so.
actually-
If something was,
Maybe I can ask a particular thing which can also somewhat close to your question. How about the SARE spectral sequence? Because I find this kind of very surprising, and
well, give me enough time and money for survival. I can probably
and
pull the
money to
entire
do what?
survival.
Survival.
I think I can
Okay.
port whatever they did in the Interactor. I need time. I also need more time to optimize the proof so that Agda won't spend like 1 hour on some proof. That's more engineering has to be done in order to make it a practical Agda proof.
I think it looks like a great conclusion to your talk. Thank you again.
support the higher industrial types of R&D. So it would actually be very interesting to see whether the cubicle type theory can now be implemented in the
It supports some higher inductive types, because there is no such thing as a higher inductive.
No,
Yes, well said.
it
Support forgetting that, right?
It supports the one that Lean uses.
It does.
Yes.
Ah, okay, that's an interesting fact, yeah. I mean,
I think we have a picture now, is that right?
That's right. They're downstairs while the sun is shining.
picture. Oh. Heidelberg, weekly gathering. Yeah, that's what I'm saying, weekly gatherings, yeah. Not weekly, lasting a week, yeah, sorry, that's, well, I wish it was a weekly. I see, okay.
You're finding this interesting?
This?
Yes.
Well, this I'm very
Well,
much source of, so.
Yes, quite.
But yes, I do find that interesting.
You go to Heidelberg this year?
I do.
Good, so we'll meet there.
See you.
I was still wondering, because I thought your answer about the resizing wasn't so clear, and I thought the original motivation for the resizing was to put profit lowest universe so that you can have the set questions and so on. But now you seem to have changed it. You just put the propositions in the lowest universe, but not prop itself.
But prop itself, you can either have it as a separate resizing rule.